So my name is Dr. Kamini Patania, and today I'm thankful to the organizers for giving me an opportunity to present my work here. The title of my presentation is Protocol for Dysprosium 3 Positive Modified NaCaVO4 Nanophosphors in Solid-State Lightning Applications, Structural and Luminescence Investigations. As you know, the combustion process here, in this work, we are presenting the combustion process which was used to synthesize the dysprosium-doped sodium calcium vanadate nanophosphors. The structural, optical, and morphological investigations were carried out with dopant concentration ranging from 0 to 3 mole%, for which various characterization techniques were used to investigate the samples. Okay, so
Hello? Did we lose you a little bit?
Okay, just hold on. Okay, so the outline of my presentation is introduction, objectives, procedure, which is further categorized into two categories, that is synthesis and characterization, and finally the results. The motivation for this work is that research and technology development at the atomic level or molecular level or the macromolecular level in this, dimension range is taking a lot of attention from the scientists and researchers working all over the world. So we are very focused and very interested to find out what is happening in this 1 to 100 nanometer range. So nanophosphors we have prepared. Why we have taken up nanophosphors? Because they possess unique physical and chemical properties due to their unique properties, which is large surface areas and nanoscale size. Distinctive properties in these materials are seen because of their quantum size effects. What is this quantum size effect? Which is caused by the confinement of electrons within particles of dimensions which is very, very much smaller than the bulk counterpart. And there are certain transitions which are not allowed in the bulk counterparts. When they come to the nano range, these transitions are allowed. And another thing is that they have a large surface to volume ratio, which give a lot of unique properties to these materials. So and what is this? What we have prepared is that we have seen that there is very scant literature available all over the world, wherein we study the dysprosium doped NaCaVO4 nanophosphors. As these are nanophosphors, the development of rare earth doped vanadates are gathering huge attention because of their high absorption, high thermal stability, and conversion efficiency from near UV to the blue spectral regions. So we have prepared sodium, calcium orthovanadates, which are being doped with the dysprosium, and the doping concentrations are basically varied from undoped to 3 mole% doping. And they have been synthesized by the low-cost combustion method, which is followed by various characterization techniques to study their structural, spectral, and optical properties to check their suitability for various applications such as solid-state lighting and display applications. So, and this is a general introduction. What are orthovanadates? Orthovanadates basically are important family of host materials due to their excellent ability to entertain a wide range of rare earth ions to make phosphors. The general formula for this type of host material is AbVO4 and Re3 positive. Here in our context, what is this A and B? A and B are basically mono and divalent cations respectively. AbVO4 is the matrix here. Re is the rare earth activator. We have used the rare earth activator, but people can also use transition metals in this type of cation.
Let me stop you for a second. You know your slides are not advancing.
Okay, sir, I am talking about this slide. That is why it is not advancing. So okay. AbVO4 have found significant application in SSL and scintillating detectors, and also for medical imaging applications. So to synthesize NaCaVO4 doped with dysprosium 3 positive, we have used a low-cost combustion synthesis process and studied its properties for various applications. And we have characterized the samples for their structural and spectral properties. And we have why we have characterized, because we want to see the effect of doped ions on the photoluminescence properties of the synthesis samples in order to find the optimum concentration of activators in the host material by studying their emission and excitation spectra. And also we want to project our material for certain applications by checking their suitability. So this is the general technique for the combustion synthesis method. What we have done here is we have taken the oxidizer and fuel, oxidizers in the form of metal nitrates and fuel in the form of urea. The weighted chemicals, that is this oxidizer and fuel, are basically collected in mortar pestle as per their stoichiometric ratios and are grounded for about 30 to 40 minutes to make a smooth paste. Okay, so then what we obtain is a pasty solution. In the chemical, we have obtained a smooth paste, and the alumina crucibles in which we have shifted our paste is then taken to the muffle furnace, which is already preheated at about 800 degrees Celsius. The combustion process will take around 5 to 6 minutes for the reaction to complete with the liberation of large amount of gases. Then we have cooled down the alumina crucibles at room temperature and transfer the powder into mortar pestle again for grinding. After this, annealing process is done at about 880 degrees Celsius in order to enhance the crystallinity of the sample. The prepared powders finally kept for the preserved for the characterization. These are the various characterization techniques that we have employed: energy dispersive X-ray spectroscopy to look out for the chemical composition, X-ray powder diffraction to check for the particle size and phase conformation, scanning electron microscopy for surface morphology, transmission electron microscopy for particle size and surface morphology, UV-vis spectroscopy to check the to find out the band gap and Urbash energy, and the PL spectroscopy to find out the emission and the excitation spectra. Results and discussions. So the first thing we want to see whether the dopant we are taking. In our case, we have taken the dysprosium 3 positive ions as the dopant, rare earth. So which it will substitute which ion in our host matrix. So for that we have to calculate the this percentage difference ratio between the substituted and the host ion. So in this case, we have seen that the atomic radii of the sodium.
Let me stop you again. Your what we see is really the first slide.
Okay. So so is this the slide you're seeing?
The title slide. Yes, that's the only one that's
okay. So can you see?
So maybe you need to scroll down, or could you go into presentation mode, or?
So I was there in the presentation mode. Can you see this now?
Now you're on the second slide.
Yeah. So I have actually talked about all these slides. So I'm here onto this. So I think it's okay. So when we see that the percentage of difference of ionic radii between the sodium and the dysprosium ion is less than 4%, so we can see that we have decided that our ion, dopant ion, will substitute the sodium ion in the sample. So the second is the EDS spectra. The intense peak of sodium, calcium, vanadium, dysprosium, and oxygen present in the spectrum confirm the formation of NaCaVO4, which is being doped with dysprosium. For elemental composition and their distribution, EDX has been analyzed. So the next is this XRD diffraction pattern of undoped and dysprosium doped NaCaVO4 nanophosphorus with JCPDS card. The phase and the structural qualities of the doped matrix were examined by means of PXRD findings. Intense, clearly defined, and prominent peaks in the XRD data suggest that the phosphors are crystallized in orthorhombic phase with a space group of CMCA, as suggested by comparison with the standard card, which is being shown on the lower side of the and then various parameters, lattice parameters ABC, volume, and crystallite size was calculated by making use of this XRD pattern. So the next is that we have calculated the particle size of the prepared sample. The average crystallite size we have used for the calculation of the average crystallite size. We have used full width at half maxima by the well-known D by Scherrer method. The formula is this DC is equal to K lambda B HKL cos theta, where DC is the crystallite size, and in this we have calculated that our crystallite size comes out to be 41.44 nanometer. So the next is that we have calculated the surface morphology by making use of the scanning electron microscope. Sir, are my slides visible now? Hello? Hello? Are my slides visible now? Yeah. So some pictures were used to examine the surface morphology, and this method is frequently employed in the characterization of the nanomaterials. So as you can see that the particles had an agglomerated morphology with irregular shapes and sizes in the nanometer range. The sample did not have a uniform shape, and we know that as combustion is a very fast method, it is employed for the synthesis of the nanophosphors, which displayed heterogeneous morphology, which might be the source of particle aggregation on the surface. As you can see, there are a lot of holes and pores on the surface of this material. So you can see it may be because of the release of gases during the combustion process. The surface is slightly rougher in texture, as evidenced by the non-uniformity in structure observed through a thorough examination of the sample. And finally, we come to the TEM transmission electron microscopy, which is showing a mixed agglomerate, and this is the TEM image. In order to determine the particle size of the sample, high resolution transmission electron microscopy of the as-synthesized nanophosphor was carried out. HRTM provides images with fine resolution drawn to a single atomic column. Nanoparticle with grain size of 42 nanometer can be seen in the TEM picture along with the fitting of the histogram. So these are the torque plots which are used to calculate the band gap of the as synthesized nanophosphors, and this is the Orbash energy calculation of the undoped and dysprosium doped nanophosphors. As you can see here, this table shows us that now what is the name of the sample, undoped to doped, up to 3 mole%. Then we have also calculated for each sample the band gap as well as the Orbash energy. The samples with low dispersion, as you can see here, the sample with the low dysprosium concentration show a widening of the band gap as we go from 3.7, 3.8. Okay, so the presence of dispersing ions may cause the band gap to change at higher amounts by making the structure less stable. Bernstein-Morse shift has been associated with this band gap widening at low dysprosium 3 concentrations, and you can see that the band gap basically varies from 3.2 to 3.8 electron volt. And with the increase of the dysprosium 3 concentration in the host matrix, the value of Orbash energy, which is basically the amount of disorder in the material, it decreases, suggesting the enhanced crystallinity with the doping concentration. So this is the PL excitation and emission spectra. The prepared samples PL excitation spectra are examined at 575 nanometer in the range from 250 to 450 nanometer. As you can see here, this is the excitation and at around 310 nanometer, and this is the emission spectra. The excitation spectra of the vanadate group display a significant peak at 310 nanometer, which is known as the VO charge transfer energy band. This band is formed in VO4 3 negative when an electron basically moves from the oxygen 2p state to the empty d state of the central vanadium ion. And you can see the emission peaks. There are 3 emission peaks, 2 very strong peaks, and there is one very weak peak also. The emission spectrum of this sample consists of 3 peaks at around 450 to 500 here, the first peak. The second one is at around 550 to 600 nanometer, and a very weak peak is also observed at around 650 to 700 nanometer, which correspond to various transitions. So you can see here I have plotted the concentration effect. The concentration versus intensity is shown here. You can see emission intensity or strength basically rises with a corresponding shift in emission peak from 0.25 to 1.5 mole%. Dysprosium ion concentration in the host matrix. After about 2 mole%, there is again increase in the intensity of the dopant till 3 mole%. Therefore, we have synthesized 2 mole samples of higher concentration, 3.5 and 4 mole%, to observe the pattern further. And we see that the decrease in intensity with the further increase in concentration, it has been observed that the greatest intensity of PL is attained at doping of 1.5 mole% of dysprosium 3 positive ions. And this is CI color coordinates and quantum efficiency. The quantum efficiency was calculated using this equation, where E lambda and P lambda denote the intensity per unit wavelength in the spectra of excitation and emission respectively. You can here we have calculated the color purity and the efficiency for each synthesized sample. The color coordinates for all the concentration of the dopant in the host matrix lie in the yellowish white region, as you can see here in this picture also. and the efficiency of the synthesized material increases with the increase in the doping up to 1.45 mole%, and after that it goes on decreasing. So the conclusions: EDX confirmed the formation of our material, which is being doped with the dysprosium, rare earth, and crystallite size was calculated by using the modified Scherrer plot, and it comes out to be about 41.44 nanometer, and it was found to be in the nanometer range. Same was employed, and it gives us the surface morphology of the synthesized nanophosphors, and TEM was employed to check the particle size. Both the morphology as well as crystallite size was estimated, and it was compatible with what we have observed in the XRD pattern. Optical band gap was estimated by making use of the Tox plots, and the chromaticity coordinates were located in the yellowish-white region of the spectra. The PL emission intensity and the quantum efficiency increases up to 1.5 mole% of the dopant concentration in the host material, and the enhanced emission intensity makes the synthesized phosphor a potential candidate to be used in the LEDs. Thank you for your attention. Thank you.
Thank you for a very nice presentation.
Thank you so
much. Are there
any
questions for the presenter? Could you go back 2 slides?
Yeah, sure.
With the morphology slide. Maybe 3 slides.
Okay, I'm coming, sir. Is this?
Slide 14 and 15, yes.
Yeah.
Right. So now, does the combustion method, does that introduce impurities? And
sir, actually,
go ahead.
Yeah.
How do you control the morphology in the combustion method?
Sir, sorry for interrupting you. Actually, combustion is a very fast method, okay? It takes around 5 to 6 minutes and sometimes less than that to complete. So when the method of growth or synthesis is very, very fast, the constituents will not get enough time to settle at their mean position, okay? So, they will, less stable. So as it is a very fast method of synthesis of materials, so sometimes, and it is also accompanied with the release of large number of gases. It's a burning kind of thing. Combustion is taking place. So that is why you can say that the holes and pores are there, and it is a little non-uniform in structure when we see it through, observation.
Can you try other methods of synthesis besides the combustion method? Can you?
Yes.
Lithography or something?
I have not tried, but these materials can be synthesized by making use of other methods also. For example, solid state solid solution method, solid state, maybe other methods also, but I have not tried, sir.
Okay.
Yeah.
All right. Well, let's thank the speaker if there's no further questions. And let's see the next speaker that we have.
Sir, I have a request.
Yes.
Sir, actually, I participated in this conference in 2021 also, but they have not given us the certificates of presentation. So this time I have a request that kindly provide us with certificates of presentations for this work.
Okay, will do.
So can you please tell this to the organizers?
I will.
Yeah, thank you so much. Thank you so much. I hope this is closed for me now.
Yes.
Can I leave? Thank you. Thank you.
Okay. Thank you.
Thank you.
Hello, sir.
Yes.
Hello, sir.
Yes.
Please, I've been trying to, I want you, just like the way you say I should upload, I've been trying to do so, but I need where to upload, mail, channel to follow.
I'll send it to you by email where you can upload your documents.
Okay, sir. Okay, sir.
Okay. Let's see. The next speaker is Gutor Simon. If you could share your screen. So I think it's possible to start sharing your screen. Sherifat, if you could stop sharing your screen, I think you are the screen sharer.
Okay, I'm in there.
Are you able to share your screen, Gota?
I'm sharing my. Can you see my screen?
Yes, it's coming. Yeah. And then you want to go to presentation
I
mode.
projected it now. I don't know if you.
Can you go to presentation mode?
Yes, I've put it on the presentation mode.
Oh, there we go. It's perfect.
Okay, you can see it clearly, all right?
Yes, I can see it clearly. You can start.
Okay. Let me try to shift this. First of all, I would like to thank the African Law Source, African Physical Society, and for organizing this wonderful conference. And to my supervisor as well. I am an MSc student at the Egypt Japan University of Science and Technology. Actually, I have, this is my second time of presenting on a global stage in this kind of negotiation. That is, I have to thank my supervisor for giving me this opportunity. And I would be saying most of the work I'm doing in the lab, of which, even though it's not yet completed, when I saw this opportunity, I feel that I could present and have most of the mentors, because I've been seeing a lot online here. So once again, thank you. So I'll be presenting on the cobalt sulfide-based biosensor anchored on graphene for continuous monitoring of glucose in sweat. First of all, this slide here is just basically I want to illustrate where I'm staying in Egypt. I'm a Nigerian, but I had a scholarship through the JICAD, which is sponsored by the Japanese government, and is situated here in Boganara in Egypt. And I don't know if you're hearing me.
Yeah, we can hear you.
Okay, so this is where the school is located, and is not far from, it's about like 400 kilometers away from Israel. And Egypt is surrounded by Libya and Lebanon. And as we all know, the Mediterranean Sea and the Red Sea, which envelop it as well. Which I travel about so many kilometers away from my country, which is Nigeria, to this place. So as you can see from here, I just want to show you, this is the professor who is supervising me currently. He's based in electrochemistry, but he has had a lot of experience in both supercapacitor sensing and other applications. This is one of the lab here, which is a gas sensing lab. Basically, the sensing lab has methane and CO2 and carbon monoxide and helium and argon. Most of the gases they sense in the lab. And here is the graphene center, which basically most of the applications here are based on graphene. Which we fabricate most of these materials using printing technology. And you see, this was right here was the pastor from Germany. He actually came to study. Was the day he came to like mount the screen printing machine, and there's the screen printing machine right here. This is a laser-induced graphene machine, a CO2 laser. This is an inkjet printer. And these are most of the electrochemical characterizations we do in the lab. And we actually use the potential stats. Here they are different models. We have the 3 electrode and the 2 electrode. And here you could see the applications for supercapacitors, sensors, biosensors. And then I will talk about the UV ozone clean later on. So as you are aware, we know that diabetes has become a global pandemic, of which that is about 5% of the world, is over 470 million people are affected globally. And out of these people, more than 11% of death occur annually. And 2% of this death happen in Africa, which is a major concern for all of us. And this is projected to even reach about 15% by 2030, according to the World Health Organization. So the demand for glucose sensors with massive sensitivity, stability, and accuracy for this improved management of diabetes has increased tremendously over the years. We are quite aware that so far enzymatic and basically the sensors that have been focused and they have been in the market so far, and the gold standard for measuring them has been blood. And actually, we never even had, if you can like check a Google check, you could see that most of the work done on sweat was during First and Second World War, of which at some point there was a slack in the process, because most of the methods were focused on sensing other biofluids like urine and just fluids. So this is also because it's even now that we are even having technology to start even thinking about sensing glucose in sweat. So because the concentration of glucose in sweat is small, which is about 10 micromolar to about 0.7 millimolar. So somebody would like the wise as a biofluid. Of course, you know that blood, as I mentioned, is the gold standard, but for continuous monitoring of glucose, how can we like monitor glucose continuously on when you are making use of blood? Because for taking blood continuously or frequently, no, I think no one will want that because of the pains attributed to that. And urine, you know that it's practically impossible for you to collect urine when you want it at the time you need it. And but it's also a good biofluid. You have saliva. Saliva is very viscous and it has a lot of contamination accompanied with food in the mouth, and the sensor has to attach to the teeth or in the mouth. We could also like have some kind of leaching that could cause some damage to the mouth. And tears is a good biofluid, but as you know, the eye is a very sensitive organ. We know that recently Google and Novartis a kind of announced the production of a sensor that is a contact lens, that both the sensing, storage, and transmission were happening on the contact lens. But I think none of us will want it to be attached to our eye like a kind of cyborg or something. So now sweat, we're interested in sweat. As you all know that basically most of the technologies now focus on designing skin patch, which we call it microfluidic technology, able to like collect sweat, do on-site monitoring instead of collecting sweat and sending the lab where during the transportation of this sweat, it could get like, there could be some kind of contamination, or even during the pour process of sweat, trying to like do it in the lab could like still lead to results that is not accurate. So we know that the skin, we have what is called the natural pump. Recently, people use the microfluidic pump, sweat pump, which they use like a kind of an injection to pass or inject sweat or but now we know that the sweat, according to literature, has a natural pump which can be able to produce sweat all over the body. We know that about over 100,000, there are more than over 100,000 chemicals reacting with more than 25,000 chemical pathways in all over the body, which you know that this, coupling with recent research, we can be able to like design materials that can monitor sweat on site. So having said that, that is easier said than done, because most of the the sensing materials, the detection techniques, and even the sample preparation are not easy to come by. So, but the good news is that we have had a lot of people who have worked in this area in recent time, and they have produced good results. Most of the results maybe will be like in the shortest possible time might be a breakthrough. You could see each of them reporting different concentrations of sweat, but you could see that most of even all of them, the range is between less than 1 millimolar. So now the focus on electrochemical glucose sensing. Why the focus? Because most of the sensing materials in literature have based on calorimetric, and the calorimetric sensing is non-reversible. That means when the color changes, you cannot reverse, which has been a big challenge. People have asked questions how you can be able to control the sensing, like which analyte actually want to sense in sweat. How can you control this? So people have asked these questions. Well, basically, for electrochemical sensors, we know that because of the redox action, both the oxidation, the reduction, it undergoes a reversible process. So basically, people use enzyme or method-based nanostructures, conducting polymers, carbon nanotubes, graphene, derivatives. In our lab, we are more focused on graphene because of its planar structure. It has a flat surface that allows and gives a very conductive path for these active materials to actually undergo a catalytic effect of glucose. So without not wasting time, this has been in most recent work. This was last week, and both of them last week. Most of the guys in our lab here has done in regards to this, using this graphene as a conducting layer. They were able to like fabricate, producing an active material that could sit on top of the graphene, and the graphene aiding the conductivity, because most of these materials, nanomaterials, have little or no conductivity. So here, this guy here used his on glucose. So someone asks me why the focus on metal sulfides, which have a little, which are in preliminary stages in literature. We know that metal sulfides have a catalytic activity, which they have a rich reserve, and they are low cost because they are abundant. Just like similar to metal oxide, metal oxide have been targeted and have been the most researched in literature on glucose sensing because of redox chemistry. And just recently, it's been discovered that this metal sulfide also have rich redox chemistry, good catalytic oxidation performance, and they are environmental friendly in a nanometer range, and they have strong resistance to poisonous species, and then they have thermal stability, even compared to this metal oxide, which is a big step. However, the poor capability and cycling stability of this metal sulfide and then the nature of agglomeration when they are in a monometallic combination. So this greatly affects the sensing properties and other applications. The result is people have, of course, like doing a kind of conducting synthesis of materials on conducting matrix, and then doing doping of other elements into the crystal lattice. So we have many materials. Please, sorry, there's something blocking the most of the headings here. I don't know whether it's in either side. If you see the headings clear. Hello?
Yeah, I don't know what you're blocking the headings on your slides. Is that what you're saying?
Yes, on my slides, like let me see if I can remove this. Okay, I have so as you can see, these are most of the components we mostly use in preparing inks, because for you to be able to do the latest technology which we deal with, the printing technology, you need to produce something like an ink to be able to print. And to do that, you need materials such as conductive fillers, which I prefer to call it functional fillers, which here you need something like an electrode, a conductive electrode to be able to print on. And then you have what they call binders. These binders are basically polymers that hold together the materials you want to print, because basically you don't want the material to spread out. And we have additives. They are like a wide range of chemicals that can easily come into either enhance the properties of these functional fillers or stabilize them to some stabilize them. Then you have solvents. Solvents are just like carrier components of your materials. With the choice of the one to use depend on the application and the target of the nano size. Basically, we use alcohols and water. So for my work so far, I'm focused on using inkjet printing, and then we have screen printing, retrogravure, and even 3D printing, but my target has been on inkjet printing. I will talk about the reason later. And these are the criteria for you to obtain an ink for inkjet printing. This is the viscosity range for the inkjet printing and the pH. Of course, you need a size below like 300 or 200 nanometers so that you don't clog the nozzle, this nozzle that you want to print, because the nozzle has a small diameter, opening, which is in picoliters. So you need ink that is not viscous. So playing with the rheology of the materials, determine the application and the printing technique you want to use it for. So like for like screen printing and retrogravure, they need higher viscosity. But here for inject, you don't need higher viscosity. So so far, I've been able to produce graphene using electrochemical exfoliation, and this basically is a cheap method which you can use the kitchen blender. So I use a source of graphite as the bulk, and then using ethyl cellulose and ethanol, we're able to like subject this for like blending for 5 minutes. That is after 5 minutes, we do this. We needed to do this for like 10 hours or 8 hours. So we're not going to do that in just a day because to save the machines as well. So blending this after 5 minutes, maybe you do like 10 or 15 minutes a day or 20, depends on the capacity of the blender. And then we're able to collect this is sonicated and then centrifuge it at 6,000 RPM to remove the supernatant. We only collected the supernatant and then added sodium chloride to make it to flocculate. After the flocculation stayed for like 24 hours, we filtered it, and here we collected the graphene. So this is the fabrication step for the active material. We mostly print on polyimide. There are different substrates, but here in our lab we basically use the polyimide because most of the material we work with sometimes need higher temperature treatment, and then for higher temperature treatment, like for graphene, which sometimes you have to need at 350 degrees, make it conduct on the polyimide. We need a software that can be able to stand that temperature within the range. Print here, I did the synthesis where I use PVP, cobalt nitrate, HCl. This PVP here is a polymer that is just coming, like I said earlier, like some kind of a binder. Or you could call it still an additive, because from both here to a kind of encapsulate the material, preventing it to grow in other phases. Then the HCl is kind of coming here like a complexing agent. It also helps in dissolving the other undissolved particles, because nanoparticles, since you're doing this at higher temperature, nanoparticles, because they are going to be in nano or micro range, they have a tendency to agglomerate. So we need this PVP, and then thiacetamide is the sulfur source. Then we use that ethylene glycol. This, because of it, double H. I think from literature, it has more enhanced properties than even ethanol. And then we add it to distilled water. We were able to print this material and the copper sulfide, of which this work is not yet published. So I've not included most of the results here. And the work is still in progress. And I just wanted to like give a talk on this. So we have, this is the camera of the inkjet printer, where you can be able to control the drop, because like I said earlier on, my focus is on inkjet because of it drop demand on printing, or drop on demand, because in biosensing you need some kind of what is called mass loading. So you need to know the actual mass loading on the working electrode of your material. So using other materials like drop casting, which somebody could actually say I use a pipette and they drop, but in reality you cannot be able to know the actual material, which sometimes it could even spread out. So this is why we're using this. So we have had electrochemical characterization. We have done the zeta potential to know the stability of the ink we made, because you know, to know the stability, the higher it is away from zero, the better, whether it is from negative or positive, which we had a good stability of the ink and the size of the material. And then we had the UV calibration. As you can see, the material increasing with absorbance wavelength, and then the concentration was in linear range, showing the stability of the material in the solvent. So sorry, my try to run here. We have recent literature, recent papers where somebody asks, okay, you are trying to make a bio a sense that could like focus what is something new that you add into that. This material here, which is chitin, we need materials that are biodegradable, disposable, because in recent time we have a challenge of climate. You can see that most countries like in Spain or some, they are even be discouraging the use of polymers. Like when you buy something, they give you plastic or something like wrapped in papers so that you can dispose and it can be consumed by the environment. So here the target is using a material that is readily available, because most of the materials used in literature based on PDMS or acrylates. They have like PDMS is flexible, but when it comes to the biodegradability, is where the issue comes from. So we can use this material, we prepare chitosan, so that we can be able to use it as a microfluidic chip to be attached to the skin. But as you know, chitosan is insoluble in water. So to prepare it, we had to like dissolve it in acidic medium to a kind of protonate it. So when you protonate the chitosan, to remove like the amino group of the chitosan, and then you make it soluble. After which you can kind of dissolve it in an alkaline medium, which this is the material in which the formation of the chitosan. What you do here basically is, after putting it here, when you protonate it, you make it, you dry it and redisperse it in an alkaline medium. When you redisperse it in this, you are kind of trying to deprotonate it again, and then centrifuge it and dry it at 50 degrees. So after drying it, we kind of make a drift channel.
You have about 3 minutes.
Sorry?
You have 3 minutes left at your time.
Okay. So here is just basically what we're trying to do. But because of the time, I don't know if this is a video, so I'll skip this, trying to like bypass using we are trying to like add a nickel foam, which could make NOH, which could, because glucose, like you know, sweat is slightly acidic, so and then slightly neutral, which you need to like raise the pH of the sweat using NOH, which is what is happening here. So we also use paper. We use chromatography paper. We kind of impregnate it with an OTS, and then dissolve it, disperse it in an hexane solution, which the paper turns like this. It becomes hydrophobic. So when it becomes hydrophobic, you cover it with an acrylate. The acrylate, you can use it to make drills, microfluidic channels, which you could expose it to UV. Ozone, we're basically using a 253 nanometer UV light, which turns the area you covered hydrophilic, and then you have your paper. And the paper is good because it bases technology on capillary action, which you don't need any pump. So this is what we expose, and this is what we have. This is the hydrophobic channels created. This is just an example to show you some. So electrochemical characterization, like I showed this before, this is the sulfide performed, and this is cobalt sulfide on graphene and polyimide. So this is an artificial swath. This is in NOH at 50 millivolt, forming a kind of a reverse bias, applying a reverse bias potential to balance pH. This, you could see the pH which at which this sense is just 12, more like a high pH kind of. So this is the last slide. Like I mentioned, I already said this, why inkjet printing? This is most of the reasons drop on demand printing, and then we need, we have low amount of waste, control the nozzle temperature, which don't need most of your materials. This impact, we have a global impact, which will not talk about this, development goals. So thank you, Christian. Thank you, sir.
Thank you. It's a very interesting talk. Could you go back to the slide where you talked about the concentration of glucose in sweat?
Yeah, am I right?
Yeah, that's the one. I missed the slide. But first, before I ask my question, let me ask, are there any questions from the audience for the presenter? So my question has to do with the thermal stability of the sensors, and whether or not the glucose itself gets complexed in other types of compounds that are not detected by the sensor that you are developing. Okay. So is there like glucose dimers, for instance, that would not be picked up?
Okay, thank you, Prof. It's a good question. Like I said earlier on, it's a work in progress. Of course, that question must be answered anywhere, anytime one is claiming to have a sensor made for glucose. Because in literature, you must perform another test, which is called interference test. So we have other analytes in sweat, such as we have other metabolites in sweat as well, which could interfere with the results. So to do that, we are still in the process of making sure that the material actually senses glucose. I have not performed that experiment, which is what I'm trying to do, which we like add other like lactase, sodium ion, and other analytes in sweat to see the calibration curve with response to glucose. So we have not done that yet, but hopefully.
Okay. There was a question in the chat. Says, how do you characterize the graphene samples? Or maybe that was from a previous talk.
Yeah. Yes. Like I said, the graphene samples, we do both electrochemical, and we have a center where we give the samples for TEM, XRD, and the rest. I think that is the question the person is asking. We do in our lab, most of the applications that we have printing technology and electrochemical measurement. So that is why you see most of the electrochemical measurements, that is as a master's student, that is what I have access to easily. So for the others, I have to submit samples and wait for to be caught. So that is why basically you've not seen the result, but we've had the results. and the ones I have easily access to. When I was looking for this opportunity to present here, I had to quickly make the slides.
Okay. Any other questions for the speaker?
Okay.
Hearing none, I think let's thank the speaker. Give him a hand clap and thumbs up.
Okay.
And if you could please upload your presentation to the website.
Okay.
PowerPoint.
Prof, sorry, Prof, you said something yesterday, which got my attention. Sorry to waste to ask this, but yeah, when somebody presented, I think the person was presenting about is it structural biology or something,
Yeah.
and then after that, Dr. Divine also made a presentation, and then you asked about the way forward if we are like trapped in a kind of a pandemic,
Yeah.
where we don't have we don't need the access from the big guns out there. So the thing, like for me, like the most things we've been lacking, like in Nigeria, I started working on temperature sensors where I had no facility that could actually, because I needed to check the lifetime emission and then of the material with the fluorescence intensity. I could not actually get that anywhere near, and it took me more than 4 years still in the master's program till I had this opportunity. So it's 4 years after, I'm starting another 2 years here, which is 6 years just in masters. So it's quite shocking. But if we can actually extend this kind of let me say technology or a kind of to countries like Nigeria and the rest, it will be a massive, because we have the scientists there, but we don't have this technology to start anywhere. Thank you.
Thank you. Okay. I see Samuel Teta is here. We're a little bit behind.
Yes, Samuel is here.
Yep. So, Goto, if you could stop sharing your screen, and then Samuel can share his screen. Okay. So Samuel, you can go ahead.
Yes, please, can you see my screen?
Yes, and you can go to presentation mode.
Yes, it's in presentation mode now.
Or you can go full screen mode. Full screen. So I think that little thing at the bottom of
yes,
that says the slide. That looks like the screen.
Yes, right, like this.
Yeah. Does that work?
Yeah, it worked for me. I'm in full screen presentation mode now.
Okay. It's not working
All right.
here. But,
oh, yes, maybe. Let me go ahead. I hope it will work.
Okay.
Good. Well, good morning here in Ghana. And my name is Samuel Tete from the Department of Chemistry, University of Cape Coast in Ghana. And today I'm here to present on prediction of polymorphism and crystallographic properties. And I'll use cinnamic acid as an example, because recently we crystallized a new polymorph of this compound. And I would like to use it as an example to show some functions in the CSD, the Cambridge Structural Database. Well, so polymorphism, as the name suggests, poly means many, and morph is forms. So you have, for example, one molecule which has been synthesized or extracted. But then when you try to crystallize this molecule, It arranges in various forms based on the crystallization conditions. You can have it in form 1, in this example, form 2, where they are cross-linked like bricks, or even it can crystallize with other molecules and sometimes with solvents, which we call solvates. And in most instances, it might not even crystallize at all, and you end up with powders or amorphous substances. This phenomenon is very, very important, or it's a center of research in pharmacy, because the same molecule, one form will be very perfect, give good efficacy. Meanwhile, the same compound in a different form will not work as required. So there is a way of predicting based on a molecular structure. There are functional groups like hydrogens and hydrogen bonding groups, which can be used using AI machine learning models to predict if really what you have is a stable form or there is a propensity for polymorphism.
Can I, your slides are not advancing. This.
Oh, I'm on slide 3. Sorry. Then I
Because I
have to
think
go back.
you're not in presentation mode. Or at least you're gonna have to click on the slides manually.
Okay. That's very unfortunate. Please let me share again.
Okay.
Yes, unfortunate. Let's go back and open. Okay. AfLS. A minute. Sorry about this. Let's go back. Oh, okay. I have it opened and share screen. Oh, share screen. Oh, entire screen. Oh, what's happening to my slides? It's refusing to share. A minute. And let's see. Zoom. Oh, no. I'll try for the last. Okay, it's opened. Select. Oh, I don't know what's happening. It's open, but
Okay. Well, share your screen again, and I think you're gonna just have to move the slides forward manually.
yeah, I open share screen. Share screen. Yes, AFL. Allow. Yes, it should be sharing now.
Yeah.
In presentation mode.
Not doing that, but
is it in presentation mode now?
No, it's not. Not that I can see. But you can just click on the slide that you need to go to. in your slide list on the left.
Okay. All right. Please, can you see the slides now?
I can see the list of slides. So just move to the slide that you need to go to.
Oh, okay. So I think it moves now.
Yeah, that moves now. Okay.
Very frustrating. All right. Thank you very much.
Mm-hmm.
Yeah, so back to the start. Yes, as I started, this polymorphism is a very big issue in pharmacy, where we have, for example, one compound, whether synthesized or extracted, that you want to crystallize. Based on the crystallization condition, you might have it in one form or a different form, the same compound, but arranged differently. And that is what gives it the form, the polymorph, as in the name. At times, this compound will crystallize with some solvent. And in such case, we call it solvate. Or in most cases, it might not even crystallize at all. And you end up with powders, what we call amorphous substances. Well, so in pharmacy, one form will work, another form might not work. And all these compounds have different properties. They have different melting points, optical properties, solubilities, and bioavailability. Because the same compound, somebody will take, it will work perfectly. Another time, it might not be efficacious. And it has happened to so many pharmaceutical industries who will have to withdraw some of their products. So there is a way, or this is a challenge in industry, to find out if polymorphism is predictable. And there are a lot of properties people use to try to predict. But today, in the Cambridge Structural Database of hydrogen bond propensity, which can be used or is being used to predict polymorphism. I'll use cinnamic acid as an example. This compound, we recently crystallized a new polymorph of it, which has been deposited in the CSD. It is an antioxidant with so many medicinal benefits. It is also a starting point for the synthesis of so many interesting compounds. So in a lab, based on the form that you have, the crystal form, it can lead to a good product if you have to use it for further synthesis, or it might delay synthesis if you don't have the right crystal form. Here are some of the polymorphs of cinnamic acid, which can be found in the Cambridge Structural Database. All these are the same compounds, but crystallized in different crystal systems. For example, the one on the top left corner, crystallized P2-C, it is monoclinic, different cell parameters. The second one, also P2-N, same compound, but different crystal systems. And the third one, the top right corner, also P2-A, a different form of the same cinnamic acid. And recently, in my lab, we crystallized the new polymorph, which is at the top or down right corner, which has been deposited. And one thing I want to show is that once you synthesize a compound or solve a structure, first it goes to the web CSD, where If you know the name of the authors or you have some identifiers, you can go and search and even download the CIF for your studies. So initially, this compound is in the web CSD, and you can enter the details and get the CIF file. This is how it looks. In the web CSD, you have the authors and a deposition number, which is given to every entry. It starts from there before later you have everything transferred to the desktop. So with this new polymorph, I will illustrate how to predict polymorphism using the CSD program Mercury. Mercury has a lot of functionalities for crystallographers who work in organic, metal organic, small molecular structures. It is the standard of crystallography. It has visualization, statistical tool you can use to study stability of crystal forms. So in the Mercury program, you have polymorph assessment, co-crystal design, full interaction maps, and a whole lot of functionalities which crystallographers can fall on, whether advanced or young and upcoming crystallographers can fall on. There are free versions, but most of the functionalities you have to pay something. But those of us in this part of the world, there are opportunities that we can apply to get access to the whole package for some time. So the hydrogen bond propensity or the polymorph prediction, it uses the functional groups of similar molecules. The molecule that you are interested in, there are a lot of groups, similar ones in the CSD. And good scientists have written algorithms, training data sets that can be used to predict whether your compound is stable. It has a propensity or ability to exist in different form, or it is just one. If it's one, then you don't need to worry. But if there's a way of it generating different forms, then there comes the worry. So this algorithm will use the functional groups to create the trained data set. And when you search, the donor groups as well as the acceptor groups will match, and it will give, in this table, under the table you see an area under ROC. It's like the line of best fit. It tells you how true your data fits the model. And if you have an ROC of more than 70%, 0.7, then you are good to go. Here, the ROC is about 0.824, and it's really perfect match for this set. So it comes out with a final prediction of a graph of hydrogen bond propensity against coordination number. And as you can see, my structure is ST11. That is the new polymorph that we have deposited. In the table down, it tells, you see red, green, and red. It says oxygen 1 into bracket D. D means donor, red, which tells you that oxygen 1 is never a donor as predicted by this model. But oxygen 1 to bracket A, see green, oxygen 1 in most of the fits is an acceptor. So these are used to predict the polymorphism. In the graph up, you see the circle on the hydrogen coordination axis. If you trace it on the mean hydrogen propensity graph, it's 0, but down there is a value for the hydrogen coordination. 0 means it is not so strong. It's not 0.0, maybe approximately 0. It's not sufficiently strong. Means there is a possibility of this molecule generating another polymorph. So in such a case, based on your crystallization condition, you have to keep to those conditions, because if you change any parameter, temperature, pressure, solvent, you are bound to get a polymorph according to this model using the hydrogen bonding principle in this model. There could be other factors, but the data set used to train this model is a hydrogen bond propensity. There are other ways of also assessing the stability of any crystal. For example, here we have the full interaction map around the cinnamic acid molecule. And we can see the areas where the donor and acceptor interactions should unite. On the map on the left, you see it. The packing on the right shows the packing, how the molecules are arranged in the unit cell or around the unit cell. If there is a disorder, of course, the map on the left, the densities will not fall in line, and we will see bends in the arrangement. In that case, the structure will not be strong enough, and there is bound to be disorder in the structure. Yes. So today, these are a few things I want to discuss with us. There are a lot of resources on the CCDC website for those who will be interested, or those young crystallographers who want to learn more. There are self-guided workshops that you can download videos, short videos, and train yourself. And if you want the full package, you can apply for the FAIR Award. This is in order of Frank H. Allen International Research and Education Program for researchers in eligible countries. Most of the countries in Africa and elsewhere are eligible. You can apply. If they see your interest in crystallography, you will be given access to the license to operate or use the CSD for some time. So within time, I'll conclude that we've been able to see polymorphs in cinnamic acid, and also the new polymorph that we found, how we can get it from WebCSD, or not only your compound, you can go there and type any author's name and get some structures for your own work. And I believe we have an idea of how to use, or how the hydrogen bond propensity works in CSD materials, as well as the full interaction maps. And I will encourage those who are interested to go to the CCDC website and learn more. I'd like to thank the organizers for this opportunity, the CSD, which gave me the opportunity to use the software, and the Xtech Lab in Benin. I believe since Monday, we've heard a lot about this facility, which trains scientists in the sub-region. I encourage all those who are interested, when the call comes, please apply and come and learn some crystallography. Thank you very much for the opportunity.
Okay, thank you.
Yes.
Is there any questions for the presenter? Gutor.
Yes, sorry. Thank you for that wonderful presentation. Mine is about what you said about going to the CCD website.
Yes.
You mentioned about those who have not had, you see, there are some free online courses,
Yes.
something like that. So like, I don't know if it is different from BioRender, because if you enter on the site and you like want to take a structure, when you take it, and maybe you want to use it, you see the website, because you have not paid or subscribed. You see the symbol of the slogan appearing on your picture or something. I don't know if it is.
Yes. There are free versions of Mercury, but it comes with a database of almost 2 million structures. But the database, there are some selected structures which you can use for educational purposes. But if you want the whole package, then you have to pay something. But you can go to WebCSD like this one. If you have an idea of the structure you want, you type in, and you can download the zip file. Once you have the zip file, you can go to the free version of the Mercury, and then you can work with that structure.
Okay.
That one is free and good to go.
Okay, thank you.
Okay.
Are there any other questions for the speaker? So in the let's see if there's anything in the chat. But in the interest of time, let's move on to the next speaker. Let's give this speaker a clap and a thumbs up. And the next speaker is Olumide JJ. Olumide, are you here?
Yes, I'm here. Hi, good afternoon.
Okay, did I pronounce your name correctly?
Sorry,
Did I
it's
pronounce
Olamide.
Olamide?
Yeah, JJ.
Okay.
Okay, please. I'll share my screen shortly. Just that my laptop is kind of loading, so I'm just some moments, please.
Hello, Prof. Good morning, sir.
Okay. I'm sorry. Can you please? Okay. Okay, so share my. Okay, so I'm trying to open up my slides.
Okay.
It's loading, please. Okay, presentation mode. Okay, just because I'm sharing. Share screen. Okay, so I'm trying to share my screen. I don't know if you can see that. Okay. Yeah. Please, can you confirm once you're able to see my screen?
It's coming up.
Okay.
I see that you started to share your screen.
Okay.
I think it's taking out. There you go. And then go to presentation mode.
Okay. Is it on presentation mode now?
It's not in presentation mode.
Okay. Sorry, where do I do that? Is it on the
It's on
PowerPoint?
the on the very bottom. If you click on the little thing that looks like a screen.
Okay.
Or if that's not working, you can go under the, I think the slideshow, where it says slideshow. Click on that.
Slideshow. Ooh. Okay, now I'm not sure. So the slideshow, is it the one on the PowerPoint itself or the one on the Zoom?
The slideshow should be on the Zoom.
On the Zoom, okay.
But what you can do is just click on the each individual slide that's in the your gallery that's on the left. As you talk, just click on the slide that you need to go to, and I think we'll be fine.
All right, so let me try and see if moving around if the slides are moving on. So I just want to give it a shot.
Okay.
So is it changing?
Doing that as you talk.
Sorry, is it changing?
I can see the I can see the outline slide.
Okay.
And okay, so now I see the outline. Now I see your title slide.
Okay. So now is it changing?
Yeah, you can just do that.
Okay. Okay, so am I good to go now?
Yes.
Okay,
you can start.
Much. Okay. Minimize this. Okay. So good afternoon, everyone. My name is Olamide Jiji. So I'm from the Protein Structure Function Research Unit, School of Molecular and Cell Biology, University of Witwatersrand, South Africa. So I'll be presenting part of my research work, which is titled Obtaining High-Yield Recombinant Enterococcus faecium nicotinate nucleotide adenylotransferase for X-ray crystallography. So part of this work or basically the work I'll be presenting is the part of my research that has actually been published. As shown here. So yeah, this is, I'll just be giving like an overview of the paper we published. So this will be the outline. I'll give a quick background of the study. Then I'll talk about how the protein was expressed, purified, and then how we crystallized and then solved the structure. And then I'll give an overview of the X-ray structure that was solved. So basically this research is actually sorry, I don't know, do you see my slides changing? Just trying to confirm.
Yes, I can see the slide.
Okay, all right, cool, thank you. So this research is actually inspired by the spike in the rate of nosocomial infection, which is caused by multi-drug resistant bacteria across the globe. And the impact of this multi-drug resistant bacteria on the public healthcare system in developing countries, especially in sub-Saharan Africa. So notably, between 5 to 10% of patients which are admitted into intensive care unit in developing countries, they acquire this hospital-associated infection, while the rate is around 21% and above in developing countries, as indicated in the map, which is indicated in brown. So we see that this country, the countries indicated in brown, they experience over 21% of this multi-drug resistant hospital-associated infection. While some other countries in the continent, they actually know about data for them. So yes, slide not changing. Oh, okay. Sorry.
You went, yeah, there you go. Slide 5. I see it.
Sorry. What do you see now? just the
Oh, now I see your full screen. So now you can just advance your
okay.
slides. Okay.
Oh, awesome. Okay, thank you. Yeah. Okay, good. Okay, so nosocomial infection is actually is known as an hospital-acquired infection, and basically this infection, they are infection that patients acquired during their stay in the hospital. So basically, they are not the patient didn't come to the hospital with that infection, but along the line during their stay in the hospital, they get infected. And then this infection includes the infections that are diagnosed within 48 hours after hospitalization, 72 hours of discharge, then and or 30 days post operation. So this infection, they're actually opportunistic. They account for over 50% of all treated cases of infection in the hospital, and its impact ranges from minor to terminal in patients. So this specific group of bacteria, which are nicknamed escape pathogens, they have actually been associated with most of the drug-resistant infections that are acquired at the hospital. And then on these pathogens, they have been listed by the World Health Organization as among the bacteria which urgently need new antibiotics. So, however, unfortunately, very few antibiotics have been developed since 2010. So, for my focus of study, I'll be focusing on Enterococcus faecium, which accounts for the second most prominent nosocomial causing pathogen in ICU patients after Staphylococcus aureus, and is also ranked the third major cause of urinary tract infection and also bloodstream infection. So, given the antibiotic resistance of Enterococcus faecium that has continued to increase over the years, and the declining number of current antibiotics that are actually effective against this pathogen. So EF, that's Enterococcus faecium, has been listed in the high priority of list of pathogens in urgent need of antibiotics, which is reason why I'm focusing on this. So oftentimes, biological macromolecules such as a protein that is central to the survival of a pathogen acts as a druggable target. So one of such potential druggable targets that I'm looking at is nicotinate nucleotide adenylotransferase. So what's so special about this enzyme? So the enzyme is actually the enzyme is an indispensable enzyme in the biosynthesis of NAD. So it catalyzes the reaction, the adenylation of nicotinamide, that is NMN and NAMN, to form their respective dinucleotides, which is NAD and NAD. So this NAD is very crucial in that most of the metabolic pathways, they depend on this NAD for generation of energy. So meaning if there's a disruption in the biosynthesis of NAD, then obviously there's going to be a collapse in the metabolic pathway, and then which would ultimately result in the death of a cell or a bacteria. So which is why we are exploring the biosynthesis of NAD as a drug target, and also the enzymes that are actually involved in the biosynthesis of NAD. So to just give us a brief background and information about the enzyme. So nicotinate nucleotide adenylotransferase belongs to the nucleotide transferase alpha beta phosphodiester superfamily, and is characterized by a highly conserved HTXGH signature motif and the presence of a Roseman fold. So basically, the structure of most of this class of protein, they have a alpha beta sheets that are actually alternating. So which is a special or it's a characteristic that is typical to this enzyme. So another thing about this enzyme is that it's a dual substrate enzyme. It can either catalyze NAMN, nicotinamide, or nicotinic acid mononucleotide. So it can either catalyze either of these substrates to form NAD. So another thing about this enzyme is that okay, yeah, this is just the chemical reaction showing the reaction that is catalyzed by the enzyme. So it either uses the NMN or the NAMN to form the dinucleotides, the respective dinucleotide, using ATP as a substrate. So it's also a globular protein, and it comprises of about 160 to 400 amino acid subunits. Most times they are, oftentimes, or those have been characterized so far, they are homooligomers. So, this enzyme is widely conserved in almost all species. However, this enzyme is actually distinct from its human counterpart in that it shares less than 20% sequence identity and no more than 40% similarity. Also, the sequence conservation, they also differ, and also differs in the quaternary structure, in biochemical and also enzymatic properties. Then also compared to the bacteria, to the human lamnat actually doesn't show preference to either of the substrates. So the human gnats can actually use either the nicotinamide mononucleotide or the nicotinic acid mononucleotide to form their respective dinucleotide or to form NAD. However, for the bacteria gnats, it has higher preference for the NMN above the NANN, so which is also good because it's important that there are distinct differences in the structure of this protein, such that when a drug is targeted at the bacteria, the human enzyme is not affected. So yeah, on to the next slide. So so far, nicotinamide mononucleotide has not been characterized in Enterococcus faecium. So the aim of this study is actually to physically characterize this enzyme and to also determine the three-dimensional structure of this enzyme. Why is this crucial, or why is it so important? Is because in order to be able to facilitate drug development or to be able to manipulate or inhibit and to design an inhibitor that can inhibit the action of this enzyme, is very crucial to actually understand the biophysical structure of the protein and to also understand, gain insight into the mechanism of biological activities of this enzyme. So that's why it's very crucial to be able to characterize this enzyme structurally, and then you can design an inhibitor accordingly. But however, before this can be done, it's very crucial to be able to have access to a soluble protein and the pure protein to be able to do a downstream characterization of this enzyme. So in our lab, we're able to express and purify this enzyme using the E. coli expression system. So firstly, the vector construct, the gene sequence encoding for the protein was obtained from the EMBL database, and then the sequence was further optimized to incorporate an hexahistidine tag. So this tag was necessary to facilitate purification of this protein. So this sequence, this optimized sequence, was then cloned into a PET11A vector, and then the vector construct was then E. coli cell was transformed with this vector construct, and then an overexpression of the protein was then carried out at 30 degrees Celsius for 6 hours with overexpression induced using a 0.5 millimolar IPTG. So upon expression of this, the cells, the protein was extracted by lysing the cells, and then the soluble fraction was then subjected to nickel ion immobilized metal affinity chromatography. So basically, when the soluble fraction is poured down into the column, because the column contains a resin which is charged with a nickel ion, the protein, the histidine, which was fashioned while the vector construct was being made, the histidine then gets covalently attached to the histidine metal, the nickel metal, and then it's trapped in the column. And while the unwanted part of the flow through, or the soluble fraction, flows down the column, and then subsequently this the trapped protein is then pulled or eluted from the column by using a higher concentration of imidazole, which competitively displays the histidine from the nickel, and then our protein is gotten. So using this method, we're able to get a pure fraction of the protein as indicated by this SDS page, which shows that we could see from the first fraction, which indicates how the different lanes, they indicate the lysate, the supernatant, the pellet, and the flow through, which indicates when the protein was still contaminated. And then the box, which is indicated in pink, shows us how we've been able to successfully purify the protein. And then, yeah, we've gotten a good fraction, a good clean, pure, and soluble fraction. to use for the characterization of the protein. So now that we have the protein, the next thing to do was to get to determine the structure of the protein, the three-dimensional structure of the protein. In order to do this, there's a need to first of all crystallize the protein, and then this was actually achieved by using various conditions, crystallization screening condition. So because proteins, they require a unique set of conditions for successful crystallization, and the only way, oftentimes, the way we do this in the lab is to use a set of conditions which has actually factored the conditions that are needed for a protein to actually crystallize. And so so this protein was actually subjected to these 96 different screening conditions from Hampton research, and then a vapor diffusion method was used to aid the formation of crystals. And then the crystals were set up using the vapor diffusion method, and the protein were dropped in this pedestal while the well was filled up with the crystallization screening condition. So this was sealed up, and then over time, this diffusion of water from the drop, which contains the protein, into the reservoir, and then the protein then gets concentrated over time, and then gradually forms crystals. So once this crystal is formed, so these are examples of or pictures of some of the crystals we're able to get from this same protein at various conditions. So we could see, and these crystals, they actually all diffracted at a very good resolution, ranging from 1.79 to about 2.5 angstroms. So yeah, upon getting these crystals, what we did next was to subject it to X-ray diffraction. And this was done at the Diamond Light Source in UK. So upon diffraction, the data were collected, and then it was processed using DAOs, and some of the crystal, for some of the crystal, the data we use DAOs, while for other we use MDSDR. So the structure solution of both structures were then executed by molecular replacement method using Mr. Bump of CCP4, and then a homology structure generated by AlphaFold was then used as a search model, and able to determine as a search model for the EF nominal structure. So before it's used, the structure was actually improved using Sculptor in Phaser. Yeah. So several rounds of refinements were then performed, and then including addition of solvents using Coot and Phoenix, we're finally able to refine the structure, and then the structure was validated and then deposited in the protein data bank. So interestingly, this is the first crystal structure to be solved for this protein, and it was actually solved at a very high resolution, as indicated in the table. We can see it's sorry. Okay, yeah. So as we can see, the APO form was resolved at a resolution of 1.9, and the adenine bound form at a resolution of 1.82 angstroms. So these are the structures of the protein, the two structures that have been deposited so far in the protein data bank. So okay, so the ligand, so okay, I'll say fortunately, because these ions, so okay, let me just the bubbles we have here, they actually, the balls, the orange and the let's say, okay, the red balls and the orange balls indicate the magnesium ions. Okay, no, the magnesium ion is indicated in green, sorry. And then the sticks represent the adenine, and then the orange and the red balls actually indicate the sulfate and the phosphate ions that were co-crystallized with the protein. So I'll just want to give us just a quick overview of the structure. So when we superimpose the APO structure with the adenine bound structure, then we saw that there were so regions which showed flexibility regions, and then these regions, they've actually been shown from literature review from other bacteria NAT that have been crystallized, and they're actually of significance. Also, another important thing to also note about the structure is that these ions, even though they are not the natural substrates of the enzyme, their presence was actually of great value in that we're able to assess the binding site, because the ions actually, or the sites they occupied, were actually the putative binding site for ATP and also for NAMN. So the superimposition of these two structures shows that adenine and the phosphate ion, they actually bind at the same site, while the sulfate ion, which is found in the two different structures, are actually occupying the same site. So we went further to do an interaction study comparing the active sites of the two structure with another gram-positive bacteria, which shares about 38% sequence similarity with this protein, and then we're able to see that these regions are actually conserved. So we see that so the binding motif which NAT uses to bind ATP is actually conserved even in the EF nano structure and in the Bacillus anthracis NAT structure. We see that the corresponding residues to histidine 41. Okay, let me just zoom it out a bit so we can see. Okay, cool. Okay, yeah. So the histidine residues, which have been shown to bind or to be productive residues that are necessary for the binding of the ATP substrate, they're actually the adenine and also the phosphate group are actually interacting with these residues, forming hydrogen bond contacts with these residues. And these residues are also evident here in the Bacillus anthracis structure, as indicated by the 2D structure, which also indicate the corresponding residues as seen here: histidine 15, glycine 17, histidine 18. So they correlate, suggesting that the particular site that the phosphate and the adenine are bound to are actually the ATP binding site. Then also, looking at the NMN putative binding site, we see that the position that the two sulfate ions actually occupy are most likely EF NAMNAT sodium NMN putative binding site. This also because this region, or the residues that are interacting with this ions are actually corresponding with those that are found in the Bacillus anthracis binding site, in the NMN binding site of anthracis. And so one interesting thing to note is that there are two residues that have been implicated in NMN binding, and these two residues are actually seen interacting with sulfate, which is the tyrosine 109 and the threonine 108. So these corresponding residues here, as indicated in threonine 85 here and tyrosine 117, they're actually interacting with the oxygen atom of the carboxylic group of NAMN. This same interaction is also observed here, as threonine is also interacting with the oxygen atom, forming hydrogen bond with the oxygen atom of the sulfate ions. So why this is important or crucial for us is that in the activity assay we did, we realized that the enzyme wasn't really active in the presence of NMN. However, in the presence of NAMN, there was much activity. So with this structure we got, it was able to tell us that the enzyme most likely have a higher preference for NAMN, as seen by it interacting exactly the same way NAMN is interacting in the beta anthracis, Bacillus anthracis binding sites. And from literature review, we know that the Bacillus anthracis is actually has higher preference for NAMN. So this actually confirms the reason why we experience lesser activity with NAMN. So for this discussion, I would just like to stop here So with this highly available structure of Enterococcus faecium NAT that we have, we are looking forward now to carrying out further structural evaluation and drug-based screening in order to be able to get structure-based inhibitors that could actually that we could work with and then possibly be designed or developed for antibiotics. So yeah, without okay. Yes, so in conclusion for my discussion, we've been able to actually establish the expression and the purification protocol to be able to get a purified EFNAT, because this is actually a major access and a pipeline to designing drugs for EFNAT in Enterococcus faecium. Also, with this high resolution structure that we have determined at 1.9 and 1.82, further evaluation can actually be carried out, and then drug-based screening to be able to design more antibiotics to fight against this multi-drug resistant bacteria. So I would like to acknowledge my supervisors, Dr. Ikechukwu Achilono and Dr. Ramesh Pandya. I also want to acknowledge my research units and then my funders. And these are my references. And thank you so much for your time and for listening to my presentation. Thank you.
Thank you. It's a very interesting talk. Are there any questions for the presenter? Where did you take your crystals to? What light source?
Oh, it was Diamond Light Source.
Diamond?
Yes, in UK.
And what was the size of the crystals, and were they they diffract pretty well, I guess?
Yeah, they did. They did diffract. They diffracted pretty well. As sorry, just trying to take my slides some few steps back. Yes, yeah. So they diffracted really well, as seen from the resolution and also the completeness of the data that was
you got 1.9, 1.8.
Yes.
That's excellent.
Yeah, thank you.
And what institution are you located at right now?
Sorry?
Where are you located right now? What institution?
Oh, University of Witwatersrand, South Africa.
Oh yeah, Wits. Okay.
Yeah.
Okay. Well, thank you for your talk. We have these monthly biophysics colloquium.
Okay.
So we will be in contact with you again to invite you to give a talk at one of those. They're the last Wednesday of every month.
Oh, okay. Thank you so much. It'll be my pleasure.
We'll be in touch.
All right. Thank you so much. And thank you for the time and the privilege to present my work here. Thank you so much. Thank you, everyone.
Thank you for coming.
All right,
let's give the speaker a hand clap and thumbs up. And if there are no questions for the speaker, let's move on to the next one. And that's Jimela Muerta.
Yeah, that's me. Can you hear me?
Yes, we can hear you perfectly. Thank you. And you can share your screen and you can start your talk.
Yeah, sure. Just a second. Yeah. Okay. Right. So, can you see the presentation?
Yes.
Okay. Right. Oh, sorry. I think I started somewhere else. Yeah. That should be. Yeah. Okay. Yeah. So, hello everyone. I am Jimela Moitro, and I work in the Indian Institute of Technology, Kharagpur. And today, the topic of my talk is it's layered high pressure, high temperature experiments with lunar iron titanium cumulate and magnesium rich mantle compositions to understand the origin of varied titanium contents of lunar basalts. So the issue in hand is that in the lunar basalts, basically the titanium variation is much larger than those seen on terrestrial basalts. It varies from about 0% to as much as 14%. So we need to know, I mean, we want to understand what could have caused this great titanium enrichment and also the variation in the titanium enrichment in the lunar basalts. So going with the most accepted theory of moon formation, it must have led to a lunar magma ocean, a global lunar magma ocean. When the experiments were performed to simulate the crystallization of a global lunar magma ocean, what was most commonly observed was that at the last stage of crystallization, the residual melt is basically very enriched in incompatible elements and in iron titanium oxides. And basically when the lunar magma ocean crystallizes, it starts with more Mg-rich compositions in the crystals, and gradually the crystals grow more Fe-rich. So basically, when we see when we go from bottom to top, the bottom layers are Mg-rich and less dense, and the top layers are Fe-rich and more dense. So there is obviously a gravitational instability, a density instability. And on top of that, when in the last stages we reach, we get a very iron titanium rich layer, melt basically that remains. And what is postulated is that the cumulus crystallizing from those melts, which would most likely be more iron rich clinopyroxene, iron rich olivine. These are minerals that commonly crystallize from those melts, and also some bit of ilmenite or rutile, that is the titanium bearing oxide phases. These might crystallize from that last FETI rich cumulate layer, FETI rich layer, melt layer. Now, the great variation in the titanium content of the lunar basalts is basically thought to be linked somehow to this last crystallizing FETI rich cumulates. So we are here in our work trying to understand whether these cumulates that were formed in the last stage of the LMO crystallization, because they were heavier, they are supposed to have undergone a gravitational overturn. Now, when it underwent the overturn, do these cumulus sink down just as solids, or do they melt on their way down? Because some theories say that the titanium in the lunar basalts might have been sourced from melts that are located at the core mantle boundary of the moon. So we need to know whether these cumulates, they could be dense enough to reach the core mantle boundary, and or else they might have just undergone melting on the way down. And if they do, whether the melts are dense enough to reach the core mantle boundary, and more importantly, whether these melts can at all generate the varying titanium contents of the lunar mare basalts. The lunar mare basalts are the titanium-rich basalts that we're talking about. So now, coming to our methods, what we have done is we have conducted a few partial melting experiments. These are the first high pressure, high temperature experiments performed in the field of geology from India using a piston cylinder apparatus at IIT Kharagpur. And the structure that we have, the assembly that we have chosen to take is a 1/2-inch talc and pyrex assembly. And the experimental design is basically, it includes, there is a bottom layer of phosphatic olivine that is taken in about 80%, that takes about 80% of the mass, and that is very Mg-rich, coming to about 92.85%, Mg number. And it is, on top of that, we have given an iron titanium rich cumulate layer, which, as given in this slide, you can see it has about 6.1 weight% titanium oxide and 39.74% FeO, iron oxide. So basically, this composition of the iron titanium rich cumulate layer, we have prepared it by mixing the high density phases like ferrite, which is iron rich olivine, iron rich clinopyroxene, and ilmenite in a 2:7:1 proportion by weight, which was similar to that obtained in the LMO crystallization experiments conducted by Rapp and Draper 2018. So with this construction, basically these are the compositions of the external compositions of our FETI cumulate layer and our San Carlos olivine, that is the phosphatic olivine layer that we have considered as the mantle, lunar mantle. It is representative of the lunar mantle, and the FETI cumulate layer is, of course, representative of the last stage remaining melt. So the rest of the conditions given, the rest of the compositions given here represent the compositions taken for similar studies by previous authors, by previous workers, basically, and they have conducted they did none of these studies tried to see the interactions between two separate layers. All of these studies basically have kind of mixed all the compositions, the phosphatic composition and the iron titanium rich compositions, and then seen the melt compositions that might come out as a result of those melting. But we are here trying to understand the interactions between two separate layers as they might have formed, as we visualize them to have formed in the later stages of the LMO crystallization. So our results are summarized in this table. We have conducted about 15 layered experiments, and they have been conducted at pressures ranging from 1 to 3 GPa, like at 1 GPa, 2 GPa, and 3 GPa. And we have got different phase relations as we have increased the temperatures at each pressure. But overall, in the subsolidus phase, we get about clinopyroxene, quartz, and ilmenite or rutile in the FETI-rich cumulate layer. And there is a reaction zone that lies under this layer, which comprises of orthopyroxene, reaction orthopyroxene, and reaction melt. And beyond that, there is the olivine layer, as we can see in this next picture. Like, this is the construction of the experimental capsule, basically. Here we have about 80% of olivine, and here is the reaction layer, and here is the FETI cumulate layer. If you zoom into this, this part, it is the reaction melt, basically, and this lies within a reaction orthopyroxene layer, and that is overlain by the FETI cumulate layer, which comprises of clinopyroxene, rutile, and in some cases ilmenite and quartz. And when partial melting occurs, the melt mostly accumulates near the top of the FETI cumulate layer. The olivine doesn't melt much, but this layer melts much faster because it crystallizes later, so it has a lower melting point, so much lower than the olivine layer. So it will melt first. Now, the major observations is that in the melt of this layer, the melts near the reaction zone, they are more Mg rich, which is expected because they are in diffusion exchange with the olivine layer, and the melts near the top, that is away from the reaction zone, they are more Fe rich. Okay, so at higher degrees of melting, what happens is, instead of the orthopyroxene and reaction melt in this reaction zone, what we get is a low iron clinopyroxene, just a low iron clinopyroxene layer, and that is then overlain by the clinopyroxene, high iron clinopyroxene and quartz with interstitial melt layer. So any melt in this region, we call it the interstitial melt. Any melt in this region, we call it the reaction melt. So at further high degrees of melting, what we have got is a melt and quartz mainly. And then in the reaction zone, what we find is orthopyroxene is back. We do not find any more clinopyroxene in the reaction zone, but we just find orthopyroxene in the reaction zone, and under that we find the olivine layer. So when we are comparing the composition of our interstitial melts with those of the lunar basalts, what we have seen so far is that these are the results from our study. At 1 GPa, the red diamond, 2 GPa, blue diamond, and 3 GPa, the maroon diamond. And these are the results from the study by Malik et al., who have conducted similar experiments with a mixed composition. So in our experiments, the results that we get are here kind of plotted in Harker diagrams, so oxide versus MgO. We can see that the SiO2 content of our melts, they are at par with the lunar basalts, almost covering the entire range of variation of the lunar basalts. These gray circles are the lunar basalts. And the TiO2 compositions, however, are generally in the higher end of the lunar basalts. Lunar basalts can have low TiO2 or high TiO2. Our interstitial mills generally have a much higher TiO2 content at par with the high Ti basalts or even higher, and not much so in the low Ti basalt zone. These are the results from the mixed composition, which were also in probably more in the high Ti zone. This is the FeO-MgO plot shows that the FeO content of our interstitial mills are at par with the lunar basalts, and but overall, in all the diagrams, we can see that our mills are low on the MgO compared to the lunar basalts, and CaO also our mills are at par with the lunar basalts, but Al2O3, the aluminum oxide, we see that our mills are much lower on the aluminum content. The lunar basalts have much higher aluminum content. And this might be caused by the bulk composition that we assumed for the moon when we formed our LMO crystallization experiments. When we decided which experiment to follow, we have considered the experiment where the bulk composition taken was similar to that of the Earth. There is another possibility of a bulk composition of moon that is much more enriched in aluminum, about 1.5 times enriched in aluminum. So that might be the reason why our aluminum content in our mills are much lower than those observed in the lunar basalts. So, but one more thing that we can see is that if we are talking about the TiO2 content of the lunar basalts, then there is a possibility that the mixing of our mills with any low Ti basalt might give us the variation, the observed variation in the lunar basalt TiO2 content. Mixing of our mills with the low Ti basalts can generate this variation. This is one point that we need to keep in mind. And the other thing is that what happens to the density of the mills that we have obtained? Now, using the Birch-Moynihan equation of state, we have tried to compute the density of our interstitial mills. Now, this is the lunar mantle density computed from seismic data. And what we can see is our mills are generally positively buoyant, that is at lower densities than the lunar mantle in most cases, except for some mills conducted at 2 GPa experiments that we have conducted, we found some mills that were negatively buoyant with respect to the lunar mantle. And so this kind of agrees with the observations that we have got in our study so far, because the mills do not generally actively percolate into the underlying olivine layer. So most of the mills just prefer to stay above. So that means they are lighter than the underlying olivine layer. Of course, the lunar mantle composition is not just olivine, it might have some orthopyroxene also. So therefore, comparing with this data, we can say that our observations match the calculated Birch-Moynihan density that we can find here. So in conclusion, basically, the preliminary calculations of the densities of the interstitial melt compositions obtained in this study show that the melts we have obtained are mostly positively buoyant with respect to the lunar mantle, and so they might not be happy to go down till the core mantle boundary. So therefore, it seems that the complete melting of the FPTI cumulates might prevent them from sinking into the deep mantle, and hence these melts might be stranded heterogeneously at different depths within the lunar mantle. So what we're trying to say is that when the last forming FPTI cumulate, those heavy cumulates underwent the gravitational overturn, they might not have gone till depths of the core mantle boundary. Instead, because they underwent melting when they were going down, the melts might be stranded somewhere within the lunar mantle. And assimilation of these melts with any low titanium basalt magma rising from the lower mantle or upper mantle might give us the variations that we have seen so far in the lunar basalt TiO2 compositions. The assimilation of these melts with low Ti basalt magmas might be the answer. These are my references. And I'd like to acknowledge my family, friends, and lab mates, of course, and the Department of Geology and Geophysics, IIT Kharagpur, CSIR India, for providing me with the fellowship for my PhD, and the AfLS and AfPS groups. These are my co-workers and my supervisors. Thank you so much.
Thank you. It's a very interesting talk.
Thank you so much.
Are there any questions for the
Should I keep
presenter?
sharing?
You can if you want. Yeah, you might. Some of the questions might have to go to the slides.
Yeah, no problem.
Is there any questions for the presenter? I had one question. I think maybe you might have covered some of these, but some of the structures, have you been able to look at whether or not any of these structures have any interesting properties in terms of band gap, photonic properties, or anything like that?
No, we have not been looking into that for now. When we did the analysis using the electron probe and the SEM, and because we do not have any such radioactive elements either, we plan to consider those when we like in the next set of experiments. We plan to include some of the radioactive elements or the the incompatible elements basically, and that those include the radioactive elements, and that might give us a few phases which can have those interesting properties. But for now, we have just considered the major elements, and no, not very interesting photonic properties. So sorry.
Yeah.
Okay,
well, thank you for your presentation, and
thank you so much for your time.
good luck with all the next phases of your work.
Thank you so much, sir.
I'll
stop sharing now.
Yep, you can stop sharing now.
Yeah.
And the next speaker is Motar. I don't know if I saw you here. Is that Motar Darkoy?
Mokhtar.
I don't see. Or let's see. Is that Mebu from the University of Kasa? Are you here? So I don't see the last two speakers. So it is probably best to just close the session. And I apologize for being behind schedule a little bit. So the next session starts at 2 o'clock at GMT plus 2 o'clock GMT plus 2. So that is 1 hour from now.
Thank you so much.
Okay, thank you.